Well, good morning. I've got a question for you. It's about the difference between a traveling wave and a standing wave. So you should read all the statements and choose one which is correct. And we have some means to assist us. This is a traveling wave. It travels, we can see when time runs, it just moves to the right. Both pictures show an actual string or a representation of a wave in a pipe. What's going to happen when it reaches the end? Well, now we observe a reflected wave traveling in an opposite direction, and according to superposition principle, we have to add them up together to get the actual profile of the actual wave, which is the, I don't know, pinkish red, not reddish, I don't know how we call it. The third one. And you can see it is not a standard profile of a wave, yet it has some kinks. But this is because what we see is interference between two actual waves, the wave which travels to the right and the wave which travels to the left due to reflection. Well, okay. And eventually a stable standing wave is generated. What kind of a wave? Well, we can see that on both ends we observe an antinode and if individual waves keep traveling, in reality we couldn't see them because on the same rope, on the same string, in the same tube, the observable would be this wave only. And in this wave, as you can see, each individual particle moves up and down like there, but the wave as a whole remains in a fixed space. And that's why we call this standing, traveling, standing. And in order to describe a standing wave, what do we do mathematically? Well, we pick a point at a certain value of x. For this x, this point travels between two maxima. That's the amplitude at point x. And within these limits, it oscillates. So the description of a standing wave should have two separate parts. One responsible for the location, second responsible for time only. They cannot be mixed together. When they mix together, the wave travels to the right or to the left. And the amplitude, the span for each oscillation depends on location. Here, the span, the amplitude is maximum, and that's what we call an antinode. And here the amplitude is just zero. That's why we don't see any motion. And let's see. What do we have here? Again, first we see one traveling wave. Now reflected, now they overlap, interfere, and eventually a standing wave is generated. If we look at this wave, one end doesn't move at all. Second moves with maximum amplitude. So this is an example of a standing wave with a tube with one end closed, fixed end, one end open. Well, now let's go back for a moment to the question. Work, willpower. So we have two equations here, and one equation has x in time, well, x and t variables represented location and time inside the same function. And second equation has those separate. And of course, the second equation describes the wave traveling. Actually, this wave should travel to the left. No, to the right. Yeah, to the right. It's a minus. It's a minus to the right. And well, technically, an equation we used looked like this. But the cosine is an even function, so it's the same thing. So this is a traveling wave, and the wave described by the first equation is the standing wave. That's it. Well, again, these are pictures which we should keep in mind. If we take several pictures, several photographs of a traveling wave, we will see how it travels, it shifts. If we take several pictures of a standing wave, it stands within the same limits, but because it oscillates, the profile changes in time. Question: if we talk about this specific wave generated in a tube with one end closed, one end open, like this one, and it doesn't generate all possible sounds, only one specific, well, several more, but we cannot see here, we can hear only one. Very difficult to find something like this. Well, I have another one. If I move the piston, I change the tone. Because, as we know, in a pipe like this, we can generate standing waves with only certain frequencies, certain wavelengths. We hear only the one which has the lowest frequency and longest wavelength, the fundamental. Now, of course, we have to make a choice between a case when the wavelength and the length related by halves, or by quarters. This is how we count. Are the halves or quarters? And the difference which basically related to this question is how we count them. For when we count halves, we count all of them, 1, 2, 3, etc., etc. But when we count quarters, we count only odd modes. And this picture clearly represents quarters. 1, 2. So 1 quarter, 2, 3, 4, 5 quarters. So first of all, for this picture, we have to use the second expression. And more importantly, it has to be the fifth mode. That's it. And sometimes, I'm not sure if WebAssign asking you or not, but just in case, there is a terminology difference between saying in a pipe or between the ends. This is the right end of the pipe, and this is the left end of the pipe. And between, we can see two nodes or two antinodes. But if we say in the pipe, in that case, we have to include the one which is on the left. So first, second, and this is one more. This is just, again, a matter of how people used to say the terminology. Now, so this was a problem which we solved, but let's do it quickly one more time. Now, let's do it vertically now. So we have a tuning fork which generates, well, sound waves. Sound waves propagate, reach the surface level, bounce off, and here we observe the interference between two waves. That interference doesn't always have to give a standing wave. A standing wave is generated only under certain conditions. And in this situation, because this end is open and this end is closed, the conditions are that this length should fit the odd number of quarters of a wavelength. And this happens twice. First time when this distance is equal to 20 centimeters. And then the level keeps dropping. And second time it happens when this distance is equal to 70 centimeters. And as we said, it means in both situations we observe a node and then another node. And the smallest part of any wave looks like this. The smallest part of any wave with two nodes close to each other is a half of a wavelength. This is 2/4 or 1/2. So this, in this region, we should fit 1/2 of this wavelength. Is it a fundamental? We don't know. Fifth? We don't know. Doesn't matter. At this point, all we know is this distance, L2 minus L1, should be equal to 1/2 of a wavelength. And that makes the wavelength is equal to 1 meter. 50 centimeters times 2, 1 meter. And that should be, that's how people measured the speed of sound, because we know the frequency of the tuning fork and the speed, wavelength, frequency related. So 340 times 1, 340 hertz. Well, in the lab you have a very sophisticated equipment. Here I don't have it. This is a way, what people used to do it, well, actually hundreds of years ago. So let's see if we can repeat it. If it's not, well, at least we give it a try. All I needed is a tuning fork. Well, actually, I don't need it. I'm tall enough. I just need to put the microphone. Let's hope it's going to pick it up. difficult for me. I'm not sure if you... Okay, now I need the third hand again. Is a standard example of the difference between physics and engineering. That's how it should look like. That's how it should work. I'm not sure what you heard because for me it was too loud. But at a certain point, because the speed of the sound is about 320, 340, and this frequency is 440 actually. That's A sharp, and at the certain column should be a little bit shorter than probably 25 centimeters. We should see, well, here see at a certain level, and here the slight increase in loudness. But if you, instead of using your ear, you use oscilloscope. The oscilloscope shows you when it happens, and you use this piston instead of the water level, move it, and when the oscilloscope indicates the maximum of intensity, that first time when the node of that wave generated by a speaker, not the tuning fork, is at the location of the piston, and then it happens again, and that's it. That is how you can measure the speed of the sound now. This is not a question. I'm going to solve it as an illustration. So this is a Blugel situation. We spin it and we're hearing different tones. And we measure, we use a microphone connected to an oscilloscope. We measure frequencies, and that's what we have. But there is no guarantee that the lowest tone we hear on this experiment is actually a fundamental. Maybe we just couldn't generate the fundamental. So we don't know what mode is that. We only know it's related to the fundamental by this equation. The mode number n, which is 210, should be equal to a certain number times the fundamental frequency. That's what we know. That's it. And now, well, this equation has two unknowns, which means we need one more equation. So we have to use the next frequency. And for the next frequency, we can write the similar equation. But if it's a next frequency, what number should we write instead of n now? N plus 1. And that's it. So we just write, well, that should be the next frequency. But now we have two equations and two unknowns. We can solve it. And the easiest way is just to do this. So it's going to be equal to n times fundamental plus fundamental. And this is 210. So the fundamental is equal to 280 minus 210, 70 hertz. And by the way, so if we, because it's a system, so we can solve for both. We can calculate n. N equals to 10 over 73. That's the third mode, actually, not the fundamental. And the next is the fourth, and the next is the fifth. So if we want to calculate the ninth by any reason, well, since we know the fundamental, we just multiply fundamental frequency by 9. And what else can we calculate? Well, if we know the speed of sound, we can calculate the length of that particular pipe. So the fundamental is equal to 70, and the speed of sound is given. That's it. So the length of this particular pipe is equal to, you have to solve it. Now, this is a 2-meter stick. This is how long it should be. This is the longest I have. "70 hertz, a relatively low frequency, and this will be equal to 340 over 14, 140, what is it? 34 over 14, 2.4, even longer than 2. That could have been an organ pipe, like this one, but much longer. Well, this is the question I want to ask you now. What is the difference? Now we're using pipe with one end closed. It still generates sound, and we still can measure frequencies. And you know the strategy, so you just have to apply the strategy, solve the problem, and choose your answer. You can talk to each other. You can discuss your strategy, your thoughts, your dreams, your sorrows. So in a minute, I'm going to switch to the WebAssign to see what you're entering. So please transfer all the information. So for now, you just ignore this question. You're calculating the fundamental. That's what you're doing right now, the fundamental frequency. Because when we know the fundamental frequency, to calculate the frequency number n, all we have to do is this. So the 9th will be equal to 9 times the fundamental, and this is our immediate goal right now. So I'm still running. WebAssign. That's a question number 4. Someone keeps answering questions ahead of the time. I wonder if it's exactly the same person again and again. So we start having a distribution. The most popular answer is 4, which is, well, good thing because it's wrong. So this is the strategy we have to apply. We don't know if it's the first mode or any other. So our first equation, of course, is this. Now we just have to use a number. 175 is equal to some so far unknown number times the fundamental. Now we are moving to the next number, 245 should be equal to next times the fundamental. And nothing is special about this. The question is, what is the next number? If the initial number is n for this type of a tube, the next number is what? Y. Exactly, that's it. So you know if the pipe is closed, numbers go by 2, 1, 3, 5, 7. If you don't know that or didn't account for that, you made a mistake. So 245 should be equal to n plus 2 times the same fundamental. Next, and odd. That's it. So next doesn't always mean mathematically next. It's physically next. And now we solve it, and the answer is 35. And now we can multiply by 9 and calculate the ninth mode. But what else can we do? Again, we can calculate the length. We just have to use the correct equation. 35, that's a new fundamental. 35 should be equal to speed, which is 340 divided by 4 times length. And what will be the fundamental of a new pipe, which is a half of the initial? Let's say we cut it. So the new fundamental frequency nu, will be equal to what? Same speed, same coefficient, but the length should be equal to a half of the previous one, which makes it 2 times previous one, 70. Sometimes we don't even need to know the actual length. Any questions? Yes? All I can say is you have to read the text of the problem and analyze the meaning of each word. And this is the word. The rest of the reasoning doesn't require thinking, it requires specific knowledge. When a pipe has one end closed, you have to count quarters using odd numbers. How do you count odd numbers? By adding to 1 plus 2, 3, 3 plus 2, 5, 5 plus 2, 7. Mathematics. Think about it. Question. At the first glance, it could be seen as impossible, but it's actually a standard musical instrument. Closed, closed. But of course, to generate some standing wave, we have holes just at a different location in the middle. And we can hear, well, we don't hear the sound generated in this tube. Due to resonance, it generates sound with the same frequency on this plate. And this excites sound around. And we can hear that length matters. Shorter, higher frequency. But if we want to calculate the frequency which we generate, we need to choose the right set of equations. And the right set of equations depends on the rule we learned, right? What should we observe at the closed end? Well, to answer this question, first we need to know the options. What are our options? An antinode or a maximum, or node or a minimum. Maximum of what? Minimum of what? Well, maximum of intensity, brightness, motion, speed. Depends on the situation. Here, of course, maximum of intensity of the pressure, so loudness. And the answer is, well, if the end is closed, we should have a node. And same here. And this basically is identical to a string with two ends fixed, which means it is identical to a pipe with both ends open. So equations are the same. We should count, and again we have to know our options. What do we count, quarters or halves? This picture clearly shows we should count halves. That's a half of a wavelength. So the relationship between the length of this pipe and modes we can generate is this. And of course, many modes can be generated, but our human ear can hear only the fundamental normally. Some people may be more susceptible and can hear the second. Well, strings. Of course, you know that not just musical instrument. Can be, you know, made from pipes, and actually closed pipe, yeah. Open. That's how it changes the frequency. Another possible instruments, string instruments, guitar, violin, they based on the fact that when we change tension, we change speed. And if the string, of course, has a fixed length, a fixed mass, but tension is different, and that affects speed, and speed, frequency, wavelength related. Wavelength is fixed by this distance. Yeah. That's how we tune it up, actually. That's pretty good, despite the fact it has been broken many, many times. We don't know, nobody knows really why we humans love music. From an evolutionary point, doesn't make any difference. But even more intriguing questions, why some people don't love it. So, this is how it works. Yeah. And of course, we just have to solve a couple of specific problems. Please read and draw the picture and copy what? 3 numbers, 75, 80, and 1320. Because on the next slide, you will not be able to read them. They will be too small. Now you have to write a statement about the wavelength. What is the wavelength of this string? What is the number? At this point, this is the most important mathematical statement we have to make. The whole length of this string is 75 centimeters. How do we know? We have eyes, we can read, we know numbers, we know units. The mass per unit length, which means the mass of 1 meter of this string, that's what we call a linear density, is equal to 80 grams per meter. Well, 0.08 in kilograms per meter. And this is the frequency number n, and we have to make a statement also about this number. N equals, is it 1, is it 2, is it 3, is it 4, 5? Can it be 4? Yes, it's a string with both ends fixed, so any n could do, but only one correctly represents this situation. Well, the first question is, what is the wavelength? But actually, these questions are related. What is n? And now, after that, the solution is routine. Yeah. Speed should be equal to wavelength times frequency. If we know the frequency and if we know the wavelength, done. And tension, speed, and linear density are related. So force of tension will be equal to speed squared times the density, which is a given number. If we know speed, that's it. What will be the fundamental? Well, we know that the nth mode is equal to that number n times the fundamental. So if we know the number to get the fundamental, we can do this. That's one way to do it. There is another way. Through the length. We always have more information than we need. If the string has a fixed length, for this string, as we know, we have to count halves. So this is how we can do it. That means this is how we can calculate the fundamental. The fundamental for this situation is always equal to doubled length of the string or a pipe. So many relationships. But now, let's vote. Yes?
How did you find n?
I didn't find n yet. That's exactly what I want to ask everybody. Did you find n? I didn't find n. This is not that n. This is not that n. This is a review from a theory. For any n, for n equals 1 or 2 or 3, we always can write this equation, including n equals 1. And that's what we call the fundamental wavelength. That's it. But now I want to ask you, what is n equal to for this wave? If you think n equals 1, please raise your hand. Vote for 2. 3. That's it. That solves the whole problem. We just have to count halves. We know that. And to know how to count halves, we know how a half should look like. Is this a half? No, that's a quarter. Is this a half? No, that's the whole wavelength. This is a half of it, 1. 2, 3. So counting says our mode is the third. Of course, we could solve it because from this equation we can calculate the fundamental wavelength, we can calculate the fundamental frequency, and the fundamental frequency, yes, is related to the actual frequency. So if this is 1320 and this is whatever number we get, we divide them, we get 3 again. But now we also can do it backwards. If we know n equals 3, we can calculate the fundamental, even if we don't need it. Yeah, that's going to be equal to 1320 over 3. Now, the wavelength. Well, this wavelength is equal to, actually, from the same equation, 2 times length divided by 3, 2/3. And you can see it, yeah, from the picture. The wavelength is shorter than the whole length by 1/3. What else? Well, that's it. That's the third wavelength, actual observed. So, and this equation in general relates the nth wavelength and the nth frequency. I'm not going to do any mathematics. That's done. Question. This is this, yes?
So is that wavelength that we just calculated, is that the wave?
That's the wavelength of this wave, the wave you observe on a string on the screen.
So it's not the wavelength of the wave?
That's I don't understand. A wave has a wavelength. A thing has a length. A thing is a string. On that string, there is a wave. That wave has a specific wavelength. And according to a definition, a wavelength of a wave is equal to the shortest distance between any 2 points oscillating in phase. For example, between 2 antinodes. That's the wavelength. Oh, sorry. 2 antinodes, that's a half of a wavelength. 2 antinodes, that's a picture which confusing. This is a wavelength. The blue one. From one antinode to another antinode in phase with the first one, in phase. And you can see to get this distance, what can you do? You can take the whole length, you can subtract a quarter from right, you can subtract a quarter from left. So that's actually another mathematical, geometrical way to calculate it. So how do we get the wavelength of this? Well, if we pretend we don't know its third, what do? It should be equal to the length minus 1/4 of the same wavelength and minus 1/4 of the same wavelength again. And now we can solve it again. It's an equation. Has one known variable, length, has one unknown variable, lambda, which goes in 3 different terms, mathematically solvable. Yes?
So how did you solve for lambda before?
By watching, by seeing the picture. Well, technically, I did it differently. This is how I did it, because I know this is the wavelength. I know it has to be equal to the length minus 1/2 of a wavelength. All right. Question to you. So that string oscillates, a standing wave, and of course for each.
So for hour, you're supposed to use the whole wave.
You're right. And we know that number. 75 centimeters.
So are you supposed to use that whole length?
That's I don't understand. That's a string. It begins on the left here. It ends on the right. And the distance between these two dots is 75 centimeters.
Yes, is that what you're supposed to use for L?
This is the string. It has a fixed length. They all have the same length. Why do they have different sound? Do they make different sounds? Because of this.
So is that what you use for L though?
You have to remember the definition. What is L? Tell me now, and we move on. What is L? If you don't know definition, this whole conversation is pointless. If you know a definition, we can talk. What is L? Or what? You answered your question. It's not the length of the equator, it's the length of this string. So distance from the point on the left to the point on the right, 75 centimeters. A physical object, string, or physical object, pipe, or physical object, tube. And inside those objects, we observe a wave, like this one. You choose your answer. Different points of this wave travel different distances. For example, what is the distance traveled by this point? 0, it doesn't travel, it doesn't move at all. This point travels certain distance, up and down, up and down. And the question is about this point, or this, or that, or this, or this, or this. Distance traveled, of course, depends on the time. So the question is, what is the distance traveled by that point, let's call it point P, in a quarter of a period? You have to choose your answer. And I have to check your choices. That's the question number 6. So anybody who answers 7 is at risk. I want to see 7. I don't want to see it. Okay. So we already have a distribution started. How many quarters does a period have? That's how we call them, quarters. So you can imagine this is just a ball on a string because there is no difference. It begins from maximum displacement from equilibrium, travels toward equilibrium, travels through equilibrium, travels back to the initial location. That's one period. That's it. So during the first quarter, it travels this distance. And this distance is equal to 2 millimeters. That's also what we call the amplitude. So in a quarter of a period, it travels 1 amplitude. That's it. How much does it travel in a half of a period? 2 amplitudes. So the answer is 2. And what is the distance traveled in 1 minute? Well, it oscillates back and forth, back and forth. Oops. In 1 period, the distance traveled equals what? 4 amplitudes, or in this particular case, 8 millimeters. That is distance traveled by this point in 1 point P, in 1 period. So, in 1 minute, the distance traveled in 1 minute should be equal to distance traveled in one period times the number of periods. How do we calculate the number of periods? Well, total time divided by the time of one period. Well, mathematically, mathematically 1 over a period is the frequency times time. So I use 8 millimeters or times 30 and 20 times 60 seconds. And that's going to be millimeters. 8 times 13, 20 times 60 equals, big number. I'm going to convert it into meters. 3.6 meters. 600 meters in 1 minute. That's the distance traveled by this little point on this string, because frequency is so high. Well, this standing wave is a combination of two waves traveling in opposite directions, and each wave has its own amplitude. Amplitude of a wave traveling to the right, amplitude of a wave traveling to the left. So when they overlap here, we have one wave and a second wave with exactly the same shape. They just travel in opposite directions. That's why the resulting wave, well, has that particular amplitude. So if we know this amplitude is equal to 2 millimeters, what should be the amplitude, which is the same for both left and right, of a single individual wave traveling to the left or to the right? What? You say something? You said something. I saw 1 millimeter. That's what you said? No. That should be a half of that. 2 over 2, 1 millimeter. Why? Because that is how we're adding waves. Yeah, remember this superposition principle. One wave plus second wave gives the actual wave. Actual. So left amplitude plus right amplitude should be given actual amplitude. Since they are equal, that gives us 1 millimeter. It's again a reminder of how an actual standing wave is built by two traveling waves which interfere with each other. Well, one. That's from the last year's line. I've changed it. Right. So very quickly, we can change the tension and generate different types of waves. So every time when change happens, we have to write equations related to situations, to both situations. So this is the initial situation. Yeah. There is a frequency, well, initial, wavelength initial, speed of the wave initial, and the related initial speed is equal to the product, but the same speed is also equal to the tension initial divided by the density initial. And we also can say that the length of this string should be equal to this number times the wavelength over 2. So this is everything we can write for the first situation. Second situation, now instead of 3, well, people call them loops, we see 2. And when change happens, the first thing we have to think about is what does not change. So what remains the same? Well, technically, all variables should have the same subscript, but the length doesn't change. We keep the same length. Where else? There's at least one more variable which is the same for both. In addition to the length. Or else? Mass or density, because density is equal to mass over length. So the initial density or final density, same strength, same length, same mass, same density. So we don't have to use that subscript. And now there is one more variable, very important variable, which is the same. We have to make that statement, and that statement comes from the text. It doesn't depend on the situation. It could have been different in different experiment, but in this experiment, it remains the same by any reason. Or else? Period. How do we know? We can read. So the period doesn't change, which means the frequency doesn't change, because frequency is just 1 over period. So now, what do we do? Well, this is what we do. We're erasing. That's the same, or else is the same. This is the same, or else is the same. This is the same. The set of equations for the second part, different speed, frequency is the same frequency, but different wavelength. And you have to keep in mind that the same letter F represents different things. A large F represents frequency, and the small f, a subscript, represents final or after the change. Yes? The speed of the wave on the string.
So the speed of the wave, like the speed of going up and down?
No. The speed for the going up and down, that's what we used to call V max. It is reached at the equilibrium. This is the speed of that wave which propagates to the right. Or this is the speed of that wave which propagates to the left. But when those two waves overlap, they interfere and they produce this standing wave.
But the standing wave doesn't, like it's standing, so shouldn't it have no speed?
Yes, but the string as a physical object provides the speed to any traveling wave on that string.
So
That's what it is. The speed of a wave on a string.
So the speed is going to be the same as the wave traveling right? And
Yes, it's the same medium, same mass, same tension. So same speed for left and right. But by changing the tension, we're changing the speed, and that changing the, in this experiment, that changes the wavelength, not frequency. How can it happen? This is how can it happen. That's the reason I'm talking about it. There is a homework problem which confuses people. In that homework problem, the frequency is fixed by the external function generator with a knob. You change the knob, you turn the knob, you change the frequency. You don't turn the knob, you don't change the frequency. In this situation, we just take it as a fact. Same period, same frequency. But if I want to finish this, and I have to, otherwise it's going to be harder on you. Less time for the next topic. So you shouldn't be asking any questions about standing waves anymore. So here, if any question arises in your mind now, you should write it down and then go to office hours or post it on Piazza. So the new speed will be equal to the new tension divided by the same density. And the same length will be equal to the new number times the new wavelength over 2. Now we have to extract some information about something. You see, so far no numbers at all. We must have some numbers. Where do we get those numbers? From the pictures. This picture, the original picture, represents a wave which corresponds to number n equals what? 3. But this picture represents to the mode with a number equal to what? 2 halves. So these are your numbers now. And there are different mathematical approaches to do it. What are we looking for? Tension. Okay. So your final calculation should give you this type of a ratio. If you do it mathematically, you're done. Or you could do it step by step, using first situation to calculate the density, and then using that number in a second situation to calculate the new wherever you need. I promised I have to, but now I'm going to do it only partially. So, what do we know about a situation when two sources drive a standing wave? We know that in the middle, we always must observe the maximum of intensity or antinode. That's what we know. Now, in this particular case, we know that the wavelengths will be equal to exactly 1 meter. That's it. Now we can start drawing a picture. So that's a maximum. So somewhere to the right, we should have the first node, and this distance should be equal to what number? It's a specific number. A quarter of a wavelength, a quarter of this wavelength equals what? 1/4, 25 centimeters exactly. So this distance represents exactly a quarter of a wavelength. Don't answer it. Which is 25 centimeters. Now we know that this distance, well, that's one of the possible approaches. I just like halves. We know that this distance should be equal to a half of the total distance between the speakers, which is 135 centimeters. And now basically we need to count how many small distances, how many 25 centimeter distances can we fit in 135 centimeters. And then you can count, well, then you can continue the drawing, and you can count, okay, not every distance corresponds to a node. Yeah. That's the second node, the third node, the fourth node. You can count just how many nodes can you fit. Or in this situation, yeah, nodes, okay. But also you can count how many antinodes you can fit in a half of the distance or in a total distance. That's geometry. Yeah, you have long distance, short distance, and you have to count how many short distances you fit in one long distance. This is a summary. This is again the summary. Now we're done with this. Now we start the last topic. We're going to talk about sound waves explicitly. This is the picture which represents how a sound wave is produced. It's just a sequence of condensation and refractions, the pressure doesn't oscillate above or below zero. No, we would die. It's not vacuum. Yeah? The pressure oscillates above and below some average value. And it reaches our ear membrane, pushes, that generates electric pulses. They travel somewhere in brain. That generates sensation we call hearing. All right, I want you to answer this question. So what's happening? You are observing the fisherman illegally catching fish by using a small explosive device to stun the fish so it explodes. An explosion takes place near the surface. So the sound from explosion travels in the air above the surface and also in water below the surface. And you're recording the sound. And the question is where it will reach you faster, in which medium microphone will pick the sound first. But the real question is, why would you even do that? So complicated. Watching fishermen, measuring sound. Something is wrong. Well, of course, the answer is practically obvious if we know that from our everyday experience, sound travels faster in more dense medium. So air, so we have an explosion, and in the air, sound wave travels at about 330 meters per second, the speed of the sound in the air. And this microphone which registers it. And the sound in water travels now faster or slower? Faster. It's actually about 1400 meters per second. So this microphone in water will register, well, we have some oscilloscope, will register the sound first, which means if we have to choose in which medium it takes less time to travel, well, of course you say in water it takes less time to travel the same distance. Well, it's just a kind of review. Yeah. The sound travels differently in different media. The more it's dense, the faster it travels. It might depend on the temperature, so we use just some convenient value. Sometimes it's 320 for air, 30, 40. That's the answer. And if we would like to solve this problem, we would have to write two equations. And that's all I'm going to do. Distance traveled. This is what we are looking for. But this distance traveled twice. It is equal to speed of the sound in air times the time to travel in air. But also same distance is equal to speed of the sound in water times time to travel in water. And now we have to write this number, the delay, which is a half of a second, should be equal to 1 time minus another time. And if we use the subscripts wrong, the whole thing is wrong. So what should we subtract from what? Time from water minus time, or air from water? Yeah, because it takes more time to travel in the air. And now you have to do some math. 1, 2, 3, 4, 5. All the information is on the screen. Well, when a sound source makes sound waves, they travel in all directions. So we have to imagine the easiest situation. The sound source is tiny, has no size, and spherical, so it pulses like this. It makes pulses, and in all directions, sound wave, spherical sound waves travel away from the source. The easiest model. So it pulses, makes pulse, then second pulse, then third pulse, then fourth pulse. And first condensation front, we call it, that sphere where all molecules oscillate in phase, we call it wave front. So that front travels away at the speed of the sound, then second, then third, then fourth. The distance between two fronts, by definition, is the wavelength. We can use some physical model to have a visual picture of those fronts traveling away. And it is always handy to have a visual model. But instead of using actual sound waves, we can use waves on the surface of water, like on a lake or. See? I changed the frequency and I changed the wavelength, the distance between the fronts. They getting closer to each other because the next front being emitted with a smaller delay. And what is happening if let's say, the sound source is moving? Well, it's hard to see. That's why we have applets which show that. And I do. And I recommend to play with those applets at home. This is a moving sound source. And you can see that because it's moving, it generates, well, it's actually moving very fast, almost at the speed of the sound. 0.88 is the ratio. So the wave fronts in front of this source shrink, which means the frequency should go up, should be higher of that sound wave. But behind the front, the wavelength expands. That means the frequency of that wave, of sound wave, should go down. Well, this is a nice model. This is a stationary source. So all fronts are spherical. But let's say it starts traveling. It makes pulses now at different locations. And because of that, the whole fronts are skewed. The wavelength in front of the source shrinks relative to the stationary case and expands, enlarges behind. Of course, we will have to first give it a name. And the name is a Doppler effect. And the most important part is to remember that for any equation which we write for the Doppler effect, like this one, everything, all variables must be related to the same observer. And how many observers might exist? Infinitely many, but only two are important. The observer which is actually measuring the frequency, and an observer on the ground, because everything is compared to the stationary situation. And stationary situation means the source is at rest relative to the ground, and there's an observer which measures wavelength and frequency, which is also at rest relative to the ground. And now, either a source or an observer, or both, begin moving. As long as they move relative to each other, we start observing the Doppler effect. And this is a source. Well, it's at rest. It's a small room, so but I can try. To move it, and I can try. That's fine. Most probably I will break it. I cannot hear myself here. When I talk, all right. So just try to tune up to the sound. Oh, I said I would break it. That's not on purpose, but every year I just miss the screen. I don't know why. I can fix it. You see, it's been broken many, many times. It actually still works. Oh, the switch is broken. Okay. In that case, I'm just going to buy a new one. Anyway. So these are the applets you can play with. And this is, again, the same statement, which is the most important physical statement. Whatever equation you write, all variables must be related to the same observer. Could have been observer running, could have been observer at rest on the ground. If you do it right, that's it. The rest comes automatically correct. So we saw this picture. If a source is moving, in front of the source, wavelength shrinks. That should bring frequency higher. And, well, it is handy to do it once. So this is t equals 1. And right here, right now, the front is being emitted by the source. But the source is moving. And let's say at t equals t2 in one period, plus exactly one period, the source has a different location. Distance traveled by the source is equal to speed of the source times time, which is a period. But during that period, the sound traveled away from the initial location and formed a new front like this, with the center at the initial location. But now the source is here. Work. Okay. And now it makes a new pulse. So the distance between these two fronts is the new wavelength in front of the source. And this is the new wavelength behind the source. And how can we relate the new wavelength and the old wavelength? Well, this is the original wavelength for the stationary source. The new wavelength is equal to the old wavelength minus or plus the distance traveled by the source. That's it. That's geometry, not physics. The new wavelength in front of the source equals old minus this distance. Behind, old plus this distance. That's it. And of course, that means minus or plus speed of the source times the period. And we know frequency is equal 1 over a period. What period, what frequency we use in this equation? Well, the period of pulses, period of the source. And it doesn't matter if the source is at rest or moving, that's the same period. So people call it stationary, 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 same. And we also know that the wavelength times frequency is equal to the speed. Now, this equation can be written twice. What is it? Prime, oops, not one, prime, prime, prime. So these are equations we write. The frequency which experienced by the observer standing, let's say, in front of the source will be different from the frequency of those pulses the source makes. Well, this is a mathematical problem, algebra. And the solution tells us how to relate the frequency of the sound experienced by the resting observer from a moving source with the frequency of the same sound experienced by a resting observer if the source would have been at rest as well. We call it a stationary situation. So this letter S sometimes means stationary, sometimes source, sometimes sound. So it might be very confusing. We have to keep track of the meaning. And this ratio is the ratio of the speed of the moving source over the speed of the sound relative to the ground under these conditions. And of course, because wavelength is different in front and behind, frequency is different. Frequency is higher in front of the source here and lower behind the source. And well, this is the summary for the Doppler effect when the source is moving and the observer is at rest. Now, different situation. The source is not moving, so the buzzer, the speaker, is at rest relative to the ground. But the observer now is running. A bird is flying. And again, every time when there is a change, at first we have to look for something which remains the same. And in this situation, it should be the wavelength. We have to imagine those fronts traveling. So you have two objects, well, front number one, front number two, they travel in the same direction with the same speed. And there's a person number one who wants to measure distance between these two objects, and there's a person number two flying above, but still measuring distance. It has to be the same distance. They use the same meter stick. So this is a very important statement that no matter how the sound wave has been generated, a moving observer and the resting observer would measure same wavelength. But why would frequency change in this situation? Now we have to go back in time. PY105, relative motion. This card represents a wave front. So there is a wave source over there. Someone screaming, ah, the wave travels away. So that's the wave front. It travels away from the source. This is the resting observer. So the speed of the sound relative to the ground and the speed of the sound relative to the resting observer, same speed. But what's going to happen if observer is moving? In this situation, the distance between an observer and the wavefront changes, well, in this situation, faster if they travel in the same direction. Doesn't want to travel to the left. In this situation, the distance between these two objects changes slower than it would have been for the resting situation. So the speed of the sound relative to the moving observer changes. That is what affects the frequency. Don't answer this question. And this is a situation when front travels in one direction. and an observer runs toward it. So the distance closes faster, which means if we want to calculate relative speed, and those are speeds, magnitudes, we would have to use this equation. What would happen if the wavefront would be traveling relative to observer moving away? Scared. I don't want to be killed. No one wants. Well, in that situation, the distance between these two moving objects changes slower relative to a case when observer would have been at rest. So we would have to use a different relationship. And we have to again remember, those are speeds, because if we want to add velocities as vectors, we would always add them mathematically, plus. Well, now we know what to do. The speed of the sound relative to the moving observer equals to the speed of the sound relative to the ground, plus or minus the speed of the observer. When it's a plus, when they move toward each other. When it's a minus, when wave wants to catch up with the observer moving away. Then we just have to calculate the new frequency. The new frequency equals new speed divided by the new wavelength, but the new wavelength is the same as the old one. We said it. And new speed depends on the relative motion. So the result is this one. This is the frequency a stationary observer would experience from a stationary source. But if they move, this variable represents the speed of the observer relative to the ground. The actual frequency changes. It goes up or down. It becomes higher when they close to each other, or lower when they move in the same direction. And this is a, well, an example, source and an observer. And finally, and I'm going to do it tomorrow in great details, of course, when they both move, we just have to combine both equations. One equation for the moving observer, second equation for the moving source, and this is, we call it Doppler effect equation, which describes all possible situations. All we need to know is when to choose a plus, when to choose a minus. And for that, we have to practice. We'll do it tomorrow. But the idea is very simple. We need to know when the frequency should go up or down. If it should go up because of this, we choose plus. If it should go up because of that, we should choose a minus to make the fraction larger. All right, thank you. Now, theoretically, you know everything about the Doppler effect. Theoretically. How would you use that knowledge? That's completely up to you. It's always the same room.
121?
Yes. So I will be there in 15 minutes. That's my standard.